Okay, welcome to identifying quadratic functions. And we'll see quadratic functions used in free flight of objects and optimization, maximizing profits, minimizing the costs, these type of things. But what we're looking at quadratic functions is what? A function where there's an x squared. They could be much more complicated, but let's start with this. And looking at this, we have a table of values. If we input these values into this function, we have -2, -1, 0, 1, and 2, some typical values to be chosen. So we just chose some values in order to graph the function to get an idea of what it looks like. So when we choose these independent values, what is the dependent value y equal? So what happens is we put in that -2, and I like to emphasize it with a parentheses. So we put the -2 in where the x goes. That -2 then squared. Well, what is negative times a negative? That would be positive. And then 2 times 2 is 4. So this works out to be a positive 4. Do the same thing with the next value as we calculate the table of values. 1 and -1 times -1 is positive, and the 1 is 1. And then 0 times itself, still 0. 1, and then 2. So 2 squared is 4. So we can take these as values, x's and y's, and graph them. And we get something that looks like this. Now notice that we've only graphed these points. The function itself has no domain listed. We can assume that the domain is all real numbers. So in actuality, this is just a sample here. We can now sketch the curve because the domain is all real numbers, and it would look a lot like this. And there we're looking at just linear equations. We're going to compare the two. If we have an input for x of 2, 3, 4, and 5, notice we're increasing by 1. The output would be 8, 6, 4, and 2. Now let's compare how much that increased. This is increasing by 1. Increasing here decreases by 2, so it increases by a -2. -2, -2, -2. This is consistent. They're all the same. It's linear. Because as this changes in certain set increments, this also follows with a set increment change, in this case, -2. So whatever the function. We can do the same thing with quadratics, but we'll notice something very unique. Let's put some input. We're given this values for the quadratic, -2, -1, 0, 1, and 2, as we increase 1, 2, or excuse me, 1, and then 1, and then 1, and 1. We're going up. That's the independent. So the dependent does what? And this is what we're going to follow in with. The dependent, these are the values we're given. Is it quadratic is the question we're asking. 4 is the output when we put in -2, and then -2, and then -4, -2, -4. The increase from here to here, well, it's a decrease of 6, so it's -6, and here it's -2. Here is +2, here's +6. So it's changing. It's not linear. This changes in a set increment. This does not. So what do we notice for quadratic? This is magical. Here's what happens. The difference of the difference is constant. Notice from -4 to -2, we're adding 4. From -2 to +2, we're adding 4. +2 to +6, we're adding 4, because the difference of the difference is the same. It is now quadratic, and that's the observation we can make for any data set. We can model a data set. We're given this values. We can say, okay, it is quadratic. So let's do an example. Let me give you an example, and you can try this on your own. So determine that the data can be modeled with a quadratic function. Give you a second here, you can pause the video. So what did you find? The difference is positive 6, positive 2, then drop in 2, and then drop in 6. That's not linear. Is it quadratic? We have to look at the difference of the difference. So from 6 to 4, it drops 4. From 2 to negative 2, it drops negative 4, and also negative 4. So that is quadratic. Let's do one more example. Here's the data that's given. And what did you find? You can pause. What did you find? The initial difference, negative 2, and then the difference of the difference works out to be just plus 1. So it is consistent. It is quadratic. The relationship between this x and this y, this is some y is some function of x squared. The happy and the sad parabola. So if I were to say, okay, this is a function of y where it's a x squared term, the y is equal to some positive something in here, x squared. If it's positive, it's what we call a happy parabola. If it's negative, the negative attitude, I guess, some function, anything in here, it has the x squared, it would be downward facing. And this is upward facing. That's where a is greater than 0. In this case, it's positive, and a is less than 0 in this case.